When you hear the word optimization, what are you thinking? Like, and not just in math. Let's optimize the blank. What does the word optimize mean? Best, right? Optimize the. Give me a scenario. I don't know. Optimize your time. Use it the best way possible, right? And sometimes that can mean minimizing the time you spend on something. Sometimes it can mean, how, I don't know how you use it, but whatever. Find the best situation. So optimizing time, it might mean you're minimizing the amount of time you spend on something. That doesn't necessarily mean it's the best like quality, right? But you've minimized the amount of time you spend on something, right? Optimize the output of some machine. Oh, you can produce more units on the assembly line. You've optimized the machine. It produces the most units. But then after you've produced that number of units, it goes down because that was the optimal outcome, right? Do you hear the word optimize, maximize, or minimize the situation? That's all this is. This is an application of the first derivative test. Good news. We might need to set up a diagram. Okay? Identify your objective. Identify your constraints. Plug the constraint equation into the objective equation. What does the word constraint mean, by the way? What's a constraint on? Let's use that example. Let's kind of run with it. We're trying to maximize the number of whatever units we're making. What's a constraint in that situation? A domain. Yeah. So maybe the domain. Okay, we can make from 0 to 5,000 units. Okay, bless you. But how many units maximizes our profit? Oh, okay. So maybe if I make, what was the upper number I said? 5,000? What if we make 5,000 units? That doesn't necessarily maximize your profit because maybe 5,000 units, you had to hire an extra 100 employees to do that. Does that make sense? You might not make the most profit because your profit curve went up and then it came back down because the profit went down because you had to increase your facilities, another warehouse. You had to increase your employees, more cost. So you might want to back up and only make this many units in that situation and stop. Just produce that many units and stop. Does it sound like economics to you? Kind of? Okay, we're not going to really get to that application of it too much. Constraint. That's a constraint. I can only make 5,000 units a day. Okay. Plug the constraint equation into the objective equation and test for extreme. This is my sequence of steps. All right. This is to help you. This is to guide you. All right. Now, we're going to start off with a problem that's very visual. We're going to start off with a visual problem, and then we're going to move into more abstract problems. All right. Where we might have to draw our own diagram. The first situation, let's try to, if we don't have a graph, we'll graph it. We have a graph for this one. A rectangle is to be inscribed under one arch of the sine curve. Okay, so here's the y-axis. Here's the x-axis. And this curve is y equals sine of x. Do you see that magenta rectangle drawn in there? That is one rectangle that could be drawn in this picture. I'll tell you what, this lesson, you guys need to really, really, really focus. I'm not trying to scare you, but these problems are not easy. All right? Once you get the setup done, pretty easy. All right, and we're going to use our calculators quite a bit. So make sure they're as charged as possible. All right, I got mine charged from the weekend. We're ready to go. So what? I'll tell you what, I'm going to open it right now, just so that 10 minutes from now it'll be done opening. All right. Step 1, do you understand the problem? We're trying to draw a rectangle in there and do what with the rectangle? Largest area. All right, so let's go through some words here. Our objective, we hear that word, the objective of this lesson, the objective of this manufacturing example, the objective of this problem is to find the maximum area of the rectangle. So our objective. If you struggle with a problem, we talked about processes for becoming a good student or staying a good student. If you don't know where to start with these problems and I check your homework and I walk around and it's blank, there's a problem. You should draw the picture. And if you have no idea what else to do, write out the objective in a sentence. I'm not saying you should do that for every problem. I'm saying if you get stuck and you don't know what to do, write out the objective of the problem in a sentence. For example, I want to maximize the area of this rectangle. That's my objective, isn't it? Maximize the area of the rectangle. So in my process, step 1, set up a diagram. Done. Step 2, identify your objective, sometimes called the primary equation. Objective equation. Objective equation. Well, that's pretty vague. Write your objective equation. Okay, sometimes it's going to be the area of a rectangle. Sometimes it's going to be the volume of a sphere. Sometimes it's going to be the surface area of a cylinder. It's going to change depending on the problem. Tell me if you can hear the objective in this problem. We are creating a new pop can that will hold 13.5 fluid ounces. Find the minimum amount of aluminum required to make the can. What's the objective? To minimize the surface area, amount of aluminum. Oh, the surface is aluminum. Surface area of a can is a cylinder. You're minimizing the surface area. See, as you piece together, even if you write it out in words first, you're piecing together what it is you're looking for, and you're narrowing down the equation that it goes with. This one's easy. We're trying to maximize the area of a rectangle. Well, what's the generic area of a rectangle? Huh? Base times height, you said? If you said length times width, I would have written that. Base times height's fine. I don't care. Either one. Everybody good? That objective is going to tell you what you need out of the picture. Let me say it again. This objective equation is going to tell you what you need to get from that picture. What 2 things do you need? You need a base and a height. If it were a can, 2 pi r squareds plus a 2 pi r h. Oh, I need the radius, I need the height. It tells you what to get from it. Okay, let's go to step 3. Identify your constraints. Do you agree the base and the height can't be whatever they want to be? Like, they can't go beyond certain boundaries, right? There are constraints. There are restrictions. Constraints are the base and the height. All right, I'm going to have you guys branch off. You're going to talk to some people nearby. I don't care if they're friends or not. You're going to work with them, all right? You're going to like it. Now, you're going to come up with constraint equations for the base and the height. I'm going to give you a hint. Think about where the sine curve hits the x-axis and think about the maximum height the sine curve takes on between those, I should say on this interval, okay? For naming purposes, think about what the height and the base need to be. These are going to be equations that are functions of x. Ready, set, go. Ready, set, go.
Interesting. Where does this subject?
Oh, I forgot to put the domain on that. Spoiler.
Yeah, what do you think?
Can I give you guys? I should have explained one more thing. Calculus is the study of rates, correct? Like we've studied rates all year through derivatives. This problem, do you agree? I drew the picture that way, but it's not a static problem. It moves. That's one example of a rectangle inscribed. Inscribed is where the top vertices are on the curve. That's the rule. The top vertices up there, P and Q, have to stay on the curve. But do you agree the largest area could come from a rectangle where P and Q are there? Do you agree with that? It could come up from a rectangle where P and Q are there. We're trying to find out what the optimal placement is for P and Q, and therefore to maximize the area. So your next hint, P and Q stay the same height. Anybody ready to give us a, now, the base is that or that. It's moving. It's a function. It's varying. It's a variable. It's an expression of x. Cool. What do you think?
I said the base would be 2x.
Okay. Any other thoughts? I'm going to address that in just a second. Any other thoughts? Is it always 2x? Because when you write an equation, it has to hold true for any situation. This is tough. Let me just first off say this is tough. All right. This is going to be the toughest part of the problem. Once you get the base and the height as expressions of x, you're golden. All right. Here we go. I think everybody in the room agrees. This is the base, correct? If you say 2x, we're going to get really existential here. What is x? Algebra 1. You're going to an Algebra 1 class today. You're teaching them how to graph. Okay, you're teaching them how to graph points. You say this is x, this is y. Okay, what's x? A position on the x-axis. If I say x is 3, what does 3 mean? It's x. But what is 3? If x is 3, 3 is, what's the meaning?
A position.
Position. But what if you're telling an Algebra 1 student, okay, go ahead and show me where x is 3. Let's keep it real simple. 3, 0. X is, where would you start off? Where would you start with your pencil? At the origin. because x is a position from the origin. It's from 0. It's how far you've gone from 0. Do you agree? That's where you start. So what if I say x is 2? Here's the origin. You're now 2 away. X is 3. Now you're 3 away. But it's not algebra 1 anymore. Now it's calculus. And if I say x, what's x? It's a distance from the origin. Are you with me? X is a distance. You can't define x another way. I'm sorry, you just can't. X is the distance from the origin. So don't call b, don't call it x. Don't call it x. Because is b a distance from the origin? No, but base it on what x is. What if this point down here, what if we say this point is x units away from the origin? Are you with me? Is that okay? To call that starting point x units from the origin? Yes. Okay. What's this length over here? X. Why? Well, sine of x is a symmetric graph. Those points on the base of that rectangle have to stay the same distance away from the zeros of sine of x. Is the base 2x? Now, what is the base?
Pi minus 2x.
Pi minus 2x. Remember the word complement? It's the complement of that. Well, if I've got x on either side of me, and the whole length, it goes from 0 to pi. If I take away an x and I take away another x, I've taken away 2 x's. Pi minus 2 x's is what's left between. Right? Doesn't that sine of x curve hit the x-axis at pi? Does that make sense to you guys? Be honest. If not, we need to talk about it. All right. I'm going to give you a little foreshadowing, okay? Just because I can see some people are still confused. You're going to see a problem like this. (16 minus x squared). Okay? A rectangle is inscribed under the curve 16 minus x squared. Find the maximum area of the rectangle. Okay, we're just going to go to the base and stop, okay? Because I want you to apply what you just learned here to this guy. Does everybody agree? This is the base. Is it pi minus 2x in this context? No. Anybody have an idea for the base of that rectangle? I'll get you in just a second. I want to see if anybody else knows. It's okay to be wrong. Okay, take a stab at it. Kaden.
8 minus 2x.
8 minus 2x. So she says the zeros are -4 and 4. And she said this length is,
X.
yeah, because we define from the origin over to this edge, we define it as x. Is 8 minus 2x correct? Did you say 8 minus 2x?
Mm-hmm.
Let's see. This is 8. This is x. What's this?
X.
X. What's this right here? 2x. This is 2x. And that's the base, isn't it? The base is 2x. So wait a minute. What's 8 minus 2x in this context? It's the little pieces over here that we don't care about. Do you see it? Be careful. That's why calculus is tough. Similar problem, different application, different setup. So what's the base that we want in this one? 2x. Why? Because the way the rectangle was drawn, this is x because of the symmetry. The base is 2x in this problem. That's all I want. I'm done. I would move on to the height. Careful though, the process that got us it here would have given us the wrong answer there because of the way it was drawn. Does it make sense? I'm glad we're addressing that now. Okay? 8 minus 2x would give us those little wings. All right. Let's keep moving on. Is everybody okay with pi minus 2x? Yes? Okay. What's the height? What's the height of this rectangle as a function of x? Or not? Call it h, yeah. But what is h? If you don't know, start off in functions of x and functions of y. Do you see how we wrote the base as a function of x? What's the height as a function of y? Cole?
Is it 1 minus 1?
What's that?
1 minus 1?
1 minus pi?
Y.
1 minus y?
Yeah.
Well, what is y? Casey?
Is it just y for the height?
The height is a y value. What's the point P? Isn't point P x comma y in general? So it's actually y in this case, not 1 minus y. What would 1 minus y give you? The height between the top and that wherever the height is of the rectangle. Make sense? So our height of our rectangle is, it's okay if you need a stepping stone, we take the height is y. But as it is, I'm going to have two variables. I'm going to have an x and a y. I don't want that. So what is y as a function of x? Cole?
Sine x.
Sine of x. It's sine of x. The height is sine of x. This is where calculus gets very existential. Right? Do you know what I'm talking about? Like, it's like, whoa, what is sine of x? It's a y value that changes. Here, sine of x is, I don't know, a third, a half, up to 1, right? So what's the height? Well, it depends on x. If x is right here, then my base is pi minus 2x, and my height is the sine of that x value. You with me? All right. Step 4. Plug the constraint equation, or I should have said equations, into the objective equation. Step 4. So our area, our objective is A equals B times H. So A equals B times H. So A equals pi minus 2x times sine of x. Base times height. We have allowed this picture to move. We've allowed it to move. We let the base be a function of x and the height be a function of x. And that rectangle can slide. And we're going to say, stop sliding when you're at the maximum area. And how are we going to find that maximum area? Well, here's our area equation. How do you maximize an equation? Huh? Find the derivative. Set it equal to 0. Get your critical points. And find out at which critical point the derivative changes from positive to negative. I've got good news for you. Calculators are allowed. We're going to graph it and look at it. Ready? Pi minus 2x times sine of x. The calculator's warmed up, ready to go. It's like, hey, I'm fresh. Your tabs aren't slowing me down. Nobody. Isn't that a song? No tabs can hold me down. Nobody. Is that how it goes? What is the song I'm thinking of?
Drag me down by one direction.
Huh?
Drag me down
Drag me down?
by one direction.
Was it talking about the tabs and the CPU?
You're playing, I don't know. But nobody can drag me down.
Huh?
The song goes,
Yeah.
nobody can drag me down.
Oh,
Nobody. I don't know if that's what you're thinking of. But
that was. It was. Thank you. Casey, I appreciate that. Those tabs aren't going to hold us down today. What was it? Pi minus 2x times sine of x. Oh, not w. X. Boom. A lot of maxes on there. A lot of maxes. You ready? We should probably go back to the drawing board. Take a look. Based on what we called x, be careful, friends, be careful. Listen very carefully what I'm about to say. Listen very carefully. Based on what we called x, what interval are we looking for a peak, a maximum value? In other words, what's the domain of our x's? Here's 0 to pi. Cole, do you agree? I disagree. The domain of our picture is 0 to pi. But x can't go up to pi. I'm sorry, x. Ready? Let's play a little game. Green light, red light. Ready? Here's x. See x? It's the purple segment. Ready? Green light. Green light. Green light. No, wait, stop. Let's try this again. Green light. Can x be right here? Yeah, if so, this is my triangle. Or nope, that's a rectangle. Ready? Red light. X can't go past the center. Because what's x? It takes. Do you agree? If I go past the center, I have no rectangle. Do you agree? X can only be, well, it's got to be more than 0. You have to come over a little bit to make a rectangle. X has to be more than 0, but it can't go past halfway. What's halfway? It can't go past pi over 2. So the domain of my x, not my picture, the domain of my x is from 0 to pi over 2. Does that make sense to you? Let's flash back to Caden's problem. Ready? Rectangle. X has to be more than 0, but less than. X has to be more than 0, but less than 4. Do you agree? On that picture, I look between 0 and 4 for my max. So ready? Menu. Window. Settings. 0 to pi. Come on. Divided by 2. That's more like it. You ready? Do you see it? Do you see the peak, the top? Menu. Analyze graph. Maximum. Oh, you mean that's been there the whole time? There it is. Again, we didn't do that in the last section because the whole calculus behind it is analyzing the derivative to make a conjecture about the original. Using the derivative. Now remember, I will say it again. Always round or truncate to 3 decimals. I know this is 0.710, and the third decimal isn't really necessary there. Did it truncate already? We need to increase your sig figs. Gotta up that float. Anybody else having that problem? Float issues? Menu. Ready, Jaden? Here you go. Menu. Settings. Float. Increase your float. What do you got right now? Probably 7? 6?
Float
3? You're only floating 3? You're gonna sink.
3 seconds.
Take that float up. 6, 7, 8. I'm floating pretty nicely at 11. I'm pretty buoyant. Whoa! Whoa! I'm about maxed out on my float. You know what? For the heck of it, let's do it. Let's do it. You get your float or go home. Float or die. I don't know. I don't want to mess with it. I only got one problem done so far. It's not good. We're not done. We're not done. Here we go. 0.710. Now be careful, friends. What's 0.710? In the context of our problem, when we graphed the function, the x value of our point represents what on our picture? 0.710 is it's the x value of this curve we just looked at, right? Are you with me? X is approximately 0.710. But what's the question asking us? Find the largest area and what dimensions? Base and height. What dimensions give you that area? Okay. Well, let's see. X is approximately 0.710. What's the base when X is 0.710? Pi minus double 0.710. Do you agree? Now, I probably wouldn't just round it to 3 decimals to type in that calculation. I'd probably take it to maybe a fourth. Okay, 0.7104. Anybody help me out? It's like 1.71 or 1.73. Help me out. Pi minus double 0.7104.
1.72.
Oh, yes. Can you give me 3 decimals just for...
0.
Thank you. I know, I'm being that guy. But a lot of you guys have gotten in a bad habit of not... Well, we haven't used the calculator a lot, but when we do, we sometimes don't round to 3 decimal places. Got the base, got the height. Now, be careful. What's the height? It's sine of 0.7104 in radians. What, 0.6 something there? We got
0.652.
Okay, I got the base, I got the height. Now, real quick, application. That's the whole point of doing this lesson. Ready? When this rectangle is 0.7104 units from the origin, are you with me? When that rectangle starts 0.7104 units from the origin, the base of the rectangle will be 1.72 units, wide. The height will be 0.652 units tall. And the area that maximizes that rectangle. Are you ready for this? The problem I graphed. What did I graph? What equation did I graph? Didn't I graph the area? So isn't this the peak of the area function? It's 1.122 units high. The area graph. So isn't that the maximum area? 1.122? 1.122 square units, I don't know, whatever, is the area of that rectangle. Does that make any sense? Now, just to be honest with you, and up front, this is calculus. Technically, that was a pre-calc question right now. Do you agree? We didn't do any calculus. I didn't take any derivatives. So what if I ask you to justify your answer using calculus? Okay. Do you agree we could take the derivative tab? Ooh, I like tabs. There we go. Fancy. Ready? Derivative, templates button, right above the multiplication, right to the right of the 9. Derivative. Come on. Derivative with respect to x of the function we just graphed, which is f1. I hit the variable button, f1 of x, or you could just type it in again. There is a maximum value on the area function at x equals 0.710 because the derivative changes from positive to negative at that critical point. So you get to have your calculator. You get to take the derivative with the calculator. You're going to tell me the critical point from the calculator. Cool.
Is it possible to use algebra for that?
Yes. It'd just get very messy. Actually, that one, it'd be kind of tough. The derivative is getting pretty messy, and it'd be tough to solve by hand.
I got to 2x or 2 sine x equals pi cosine x minus 2x
Yeah.
cosine x.
Yeah, you'd have to inverse. Tomorrow, I have news for you guys. The cans you drink pop out of, if you drink pop, they're not optimized. They're wasting aluminum. We're going to maximize them tomorrow. We're going to solve this riddle. Okay? Tonight's homework. Only 3 problems. Page 226, 5, 6, and 7. Page 226. 5, 6, and 7. My hint to you for 7, you got an 8 by 15 piece of cardboard, and you're going to cut out corners. You probably did this last year in pre-calc, yeah? Cut out corners, and then fold up the sides to make a box. You're going to maximize the volume of that box. I will give you a hint. You're going to cut out X by X corners. X by X corners. Just don't cut any corners in your homework.
I have to take that quiz.
Yes, you do.
So, can I take it today? Like 7th period?
7th is perfect.
Really?
It is